Hey, Nyla. Hey, Mohammed, great to see you. How's it going?
It's going.
Good day? Good. Wonderful. All right. We'll wait just a second. Everybody to get here? Here comes Bella. All right. How are you, Bella? AC, nice to see you. Remember, you guys have to have your cameras on, unless I get permission from your parents for you not to. So that's just AIM Academy's policy. I don't always do the greatest job enforcing that, so I'm going to try to remember because it is important. All right. Anybody have any questions? All right, hold on one second. Okay, if nobody has any questions, we will go ahead and get started. May have a few more students joining us. Nobody has written to say they weren't coming today. So let's begin. Okay, hopefully you can all see that where it says physical science. All right, great, wonderful, wonderful. All right, here comes Wick. All right, so we are today going to spend, So one thing I want to remind you guys, if you haven't looked ahead in the lessons, is that on Wednesday, November 20th, so that's the week before your Thanksgiving break, you're going to be doing some oral presentations. So there's information about it in the lessons. You can see the choices that you have. You have 4 different choices that you can use. Actually, let me just for a second here drag this in so you guys can see what it is that I'm talking about in case you haven't looked at it yet. So you'll have a science option, history, social studies option, a language arts option, and a math option. So let me show you what I mean. We'll drag this in and come down here to Unit 6. And you can see here, instructions for, so yours will be this one here, instructions for an oral presentation. It's the week of November 18th. So for you guys, that'll be Wednesday, the 20th. So all the information that you need is right here. It's going to be about SOAP. So I've got a lot of information for you there. And then down here are your options. You'll do a science option. It'll tell you what to do. You're going to make homemade soap, and then it'll tell you what you have to do for your presentation. The social studies option, what to do, what you do on your presentation. Language arts, what you do, what your presentation is, and math, how you calculate a year's supply of soap and what you do for your presentation. And then if you look right here, how will this be graded? You can see the rubric in this lesson called Your Grade for the Oral Presentation. And right down here at the bottom is a rubric that will tell you what you need to get the most points for all of the categories, and then what you get if you don't do your best on all of these categories. Okay, so again, that will be for you guys. It will be on November 20th. So make sure that you take a look at that. All right. All right. So today we're going to talk about some basics of science, some things that we need to know for all sciences. So what do you think of when you hear the word science? What does that word mean? Anybody have a thought what science means? Nyla,
The study of our world.
that's excellent. The study of our world. Yeah. A study is a way of knowing about the natural world. And we study it using evidence that we get from often experimentation, observation, and then we, of course, use logic too. Now, what do you think of when you hear the word physical science? Go ahead, Nyla.
Like gravity and stuff like that.
Yeah, that's one of the things that we study. Basically, we can divide physical science up into two main categories: matter, that we're learning about this first semester, and then energy, which we'll learn about next semester. So, but gravity, of course, is one of the forces that's at work. So that has to do with both matter and energy. So there's a lot of different fields in science. Good, Allison, physical aspects of the earth, great. So there are a lot of different fields in science. One of the things about science, though, is that it's always changing. Wick, do you have a question?
Yeah, so I know the difference between mass and weight. Is matter weight or is it mass?
So matter is anything that has mass and takes up space. So matter and weight are different from each other. Matter and mass are different from each other, and mass and weight are different from each other. It's kind of like saying, is a glass a plate or is it a fork? Well, they're all related. They're all things that we eat with, but they're not each other.
Okay.
Does that make sense? So something is made up of matter. Matter is the particles, the atoms, the molecules, the compounds that things are made of. All of those particles have mass. So they have, on Earth, we equate mass with weight because, well, there you can use them the same. Mass is basically the content of all of those particles. What are all of those particles made up of? How much do they, what impact do they have? It's kind of hard to not use the word weight, because on Earth, when we use the word mass, we can use weight. But of course, you have the same amount of mass if you go to the moon, but your weight is going to be very different on the moon than it is here on the Earth. So there are three different terms that have three different meanings. Does that make sense? Okay, good. Good. Remember, guys, that you're supposed to turn your cameras on. All right, you have to leave your cameras on unless your parents ask for permission. So if you have a reason that your camera can't be on, by all means, have your parents write to me and let me know. But I have to enforce that, and I'm going to start doing so. All right. Now, like I said, all of science, no matter what field we're talking about change, because science changes always. Our ability, our knowledge of the world is always expanding and growing. Now, sometimes that change can come real quickly in just one big step. We can learn something that we didn't know before that changes things. Often it's slower, sometimes even tiny little baby steps. Sometimes, though, new ideas that people come up with are not easily accepted. So sometimes scientists can even be mocked or made fun of or ridiculed for their new ideas. Can you guys think of a time when that happened? Can you think of any examples of a scientist's work not being accepted? AC.
It's not exactly science, but the guy who thought the Earth was not the center of the
Yeah.
universe, but the sun was the center.
Yeah, exactly. So that is definitely science. That is astronomy, which is a scientist. So Copernicus was the one who introduced what we call the heliocentric model. We'll learn about that when we get into the second semester. Maybe, I think we do learn about that. But basically, he said everybody until him thought that the Earth was the middle and all the planets in the sun revolved around the Earth. Well, you can see why they thought that. It looks like it. When I stand on the Earth and I watch, it looks like the sun's going around us. But he proposed that the sun is the center and all the planets go around the sun. And nobody believed him at the time. He had a lot of trouble at the time because people thought that that was a very wrong idea. Wick.
There was another mathematician who said basically it was kind of like a challenge problem that one mathematician brought up, and another mathematician, after the problem was solved, uh it was like how light moves, and um he said that light always moves in the like smallest path possible. So people ridiculed him and they didn't think that was possible. Like they thought, oh, nature wouldn't care anything about that. But Euler supported him, and then they finally found out some formula.
Yeah, that's a great example. That's a really good example. So there's a lot of those in history. One of them is what we call the germ theory. So until this guy named Joseph Lister came around, doctors would go right from doing an autopsy on a person who had died of a disease. So an autopsy is where they cut open the body to see why they died. And they would go right from there. They'd kind of wipe their hands on their coat and then go and help somebody, a woman, give birth. And everybody wondered, why is there such a high death rate among mothers and new babies? And he said, it's because there are germs that you're carrying from the autopsy to the labor room. And nobody believed him at the time. Well, now we do. Now we know that. We know that germs can be passed from one person to another, but that wasn't accepted in his lifetime. So those are just a couple good examples. And yeah, Galileo, AC, yep, absolutely. So that's one thing that science all has in common, is that it's always changing. And we have to, as scientists, be open to having our ideas challenged, to having our ideas even disproven, because that's really what science is all about. Science is about trying to disprove some of the ideas that we have. So another thing that science fields all have in common is that scientists like to investigate. So investigation is the term that we use to explain how scientists add new knowledge or gain a better understanding of the world. So it gives us evidence that helps to answer questions. Sometimes, even if the evidence, even if the way your experiment turns out doesn't help to prove anything or give an answer to anything, it may still be useful because it might lead to new questions or new ideas for an experiment that you would do. So as more and more knowledge is discovered, science continues to advance. I like to say to students that we often learn more from experiments that don't work than we do experiments that do. Because if the experiment works, if it does what I thought it was going to do, then I'm just done. And I don't really think about it much anymore. I move on. But if it doesn't work, I tried to solve that. I wonder why it didn't work. I wonder what the problem was. What could I do differently to make it happen differently the next time? And I can sometimes learn more that way. So, of course, scientists use different ways, different methods in order to explore the world, in order to understand the world. But there are a couple of steps, a general pattern that most scientists follow. And that's what we call the scientific method. You can see the steps of the scientific method right there. So the scientific method itself, a good definition of it is the process used to find answers to questions about the world around us. All right, so is there only one scientific method? No, the answer to that is no. There's more than one. There's different versions of it. So some versions might have more steps than I have right here. Some of them might have fewer steps than I have right there. But they're all going to begin with this basic pattern, the basic step or sequence that we follow in order to answer questions. What it gives us is it gives us an organized method for conducting and analyzing an experiment. So I want to look at all the steps of the scientific method today, and then we'll try to use what we learn to solve a couple of cases, or rather to answer some questions. Wick.
Yeah, so for the recent optional experiments, I've been trying to do them, but I can't find all of the resources. So is there any place where you would recommend me to like get the like for the color density thing, how they had in the video, like those things, the circular thing, do you know any kit or something?
I don't have a kit for the class this year. I'm working on that for next year. I know that doesn't help you now. But if you write to me, Wick, after class and tell me what exactly it is that you're looking for, I can make some suggestions on things to use. Okay, because it's different depending on which experiments you're talking about. But all of you, not just Wick, if anybody has trouble finding anything, let me know. And I can always find some websites or locations that you can find things. Okay, all right, so let's look at the steps of the scientific method. So starting at the top, our first step is going to be observation. We observe something. An observation is information that we get using our senses. So think of what your senses are: your sense of sight, sense of smell, sense of taste, although never taste anything in a science experiment unless you're told that it's safe to do so. We can hear, we can feel with our sensors that are in our skin. So we see with our eyes, we hear with our ears, we touch with our hands, we taste with our tongue, we smell with our nose. So anything that you get using your senses is an observation. We can also extend our senses though. We can use equipment, technology, if you will, to extend our senses. Can you name some kind of equipment that we would use to extend our sense of sight? To be able to see something that we can't normally see? AC.
A microscope or a magnifying glass.
Yeah, excellent. They make things bigger. What about the other way? What else could we use? What other kind of equipment could we use to extend our sense of sight? AC.
A mirror.
Mirrors sometimes, yeah. Mirrors sometimes are a good tool that we can use. I was thinking telescope. You know, a telescope brings something closer that's really far away. So it makes it bigger, where it makes this bigger thing small enough that I can see it with my eyes. Excellent. So thermometers are another example. Computers can extend our senses a little bit. All right, so what I want to do to walk through these steps of the scientific method, we're going to use a real life example to talk about the different steps that we have. All right, we're going to use a blacksmith. So suppose there's a blacksmith who reads an article about a new type of synthetic fuel that will make a hotter fire. What was the observation? Wick.
He observed that you can get better fuel for the fire.
Good, good. The observation was that there might be this new type of fuel that's available. Might be better for my fire. Okay, the next step then is question. What question might the blacksmith ask? Wick.
Will it really make my fire burn better, or will it just be the same?
Excellent, excellent. Is it true? That might be what the blacksmith would ask. AC.
The price or availability.
Yeah, they might want to know the price and availability. That's definitely true. Allison.
Like what he would need to like make it happen, or
Yeah.
like what he would have to do.
Yeah. What do I need to do in order to try this out? Good, good. So the next step then, after asking questions, is to do a little bit of research. So maybe the blacksmith would go to the library, or would go to an internet, or would talk to an expert and get more information about this. Maybe somebody else has already done some experiments to test this out. But let's suppose that our blacksmith says, I want to test it out for myself. I know what other people are saying, but I want to give this a test. I want to do an experiment myself. Well, the next step after research is to formulate a hypothesis. So anybody know what a hypothesis is? Nyla.
It's like an educated guess.
Good, very good. I like the term educated prediction, but educated guess is the one that you'll read most of the time. And that's a good way to think of it. It is an educated prediction. It's educated because it's based on your observations and your knowledge. And it's a prediction about what you think is going to happen. So a couple things about a hypothesis. A hypothesis has to be testable. For it to be useful to us as a scientist, it has to be something that we can run a test, we can run an experiment to see if it's true or if it's not. If a hypothesis cannot be tested, it's not scientific. So think about this sentence here. There are invisible creatures all around us that we can never observe in any way. Is that testable? No. If they're invisible and we can never observe them in any way, there's no way for us to test it. Now, it might be true, but we can't test it. So it's not a valid scientific hypothesis. So there have to be ways that we can make observations that lead to questions, that lead to testing in order for something to be scientific. And it also must be what we call falsifiable. So that means it has to be possible to show that it's false. If it really is false, there has to be a way to show that. So this is where I'm talking about science changes. As scientists, we're always trying to disprove things. That's basically what science is about. We're trying to prove that something that we think might not be true. Because if we can't prove that it's not true, then we have to accept the possibility that it is. So think about this sentence. There are other planets in the universe where life exists. Is that testable? Yeah, that's testable. We could theoretically send a craft out into space and look in other places in the universe. We could run a test on it, but is it falsifiable? It is not falsifiable because that spacecraft may never find an inhabited planet. It might look for 1,000 years and never find a planet that has life on it, but that doesn't necessarily mean there isn't one. The universe is vast, right? It's huge. We're never going to be able to check every single planet for life. So it's testable, but it's not falsifiable. Wick.
Another reason why it's not falsifiable is because the universe is ever expanding.
That's right. That's right. Yeah, and Allison, you're right. They might be hiding. Yeah, they might not want us to find them. That doesn't mean they're not there. Good point. All right, let's look at this little example too now. Let's suppose this sentence. Any two objects dropped at the same time from the same height will reach the ground at the same time, assuming the absence of air resistance. So there's nothing slowing them down. Is that testable? Yeah, that's testable. We could do it. We could drop two objects at the same time from the same height, and we could observe when they reach the ground. Of course, we'd have to make sure there was no air resistance on one, so that's important. But that kind of test is possible. In fact, we could do it over and over and over again. AC.
You could do it on the moon.
We could do it on the moon. Yep. No air
They actually
resistance
did.
there.
I think Apollo 16.
Yep. So is it falsifiable if it really is false? Yeah, it is, because we could easily test many different combinations of any two objects. If ever one time we drop two objects at the same time from the same distance and one of them hits the ground first, that's false. We have an ability to falsify that. All right. Now, the last thing about a hypothesis, whenever possible, you want to write a hypothesis in what we call if-then format. So if-then format is really, really important because it tells you what you're going to do in your experiment and what you're going to look for your data. So let's say that I wonder if I will do better on my exam if I get a good night's sleep. I could write my hypothesis like this. If I get at least 8 hours of sleep, then I will do better on my test. See, that tells me what I'm going to do. My test is going to be getting a good night's sleep, getting 8 hours of sleep. What I'm going to look for is my grades on my test. What if I suppose that drinking coffee before bed makes it take longer to fall asleep? If I write that in if-then hypothesis, if I drink coffee before I go to bed, then it will take me longer to fall asleep. That then tells me what I'm going to do. My experiment is drinking coffee before bed. My then is going to be taking longer to fall asleep. Wick.
Wait, but technically you have to do that for one day you have to not drink coffee, and the other day you have to drink coffee to compare it to see if you
Yes.
take longer to sleep.
Absolutely.
Isn't
We
it
need to have a
already
control.
proved? Isn't it already proved that when caffeine reaches your brain, that the melatonin won't go in, so
Yeah.
it'll take longer to sleep?
Yeah, there's a lot of reasons that caffeine is not good for a person after like noon. Most people. So caffeine has what's called a half-life. We're going to learn about half-life when we start talking about radioactivity, because all the some elements have half-lives too. But a half-life basically means how long does it take for it to be broken down into something else. Well, your body will break caffeine down. It'll separate the molecules in caffeine into individual atoms. But how long does it take to do that? Well, it takes about 6 hours to break down half of the caffeine that's in your body. So let's say you have a cup of coffee and it has 50 milligrams. I'm just making that number up, 50 milligrams of caffeine. That means that 6 hours later, you still have 25 milligrams of caffeine in your body. And then 6 hours after that, you have 12 and a half milligrams. So now we're looking at a half a day, 12 hours, that's half a day. So yeah, caffeine is not good for you in a lot of different ways. Yeah, but Wick, your point is a good one. We always need to have a control group. And that's what we're going to do when we get to the experiment part. We'll talk about the control. So when we're just talking about the hypothesis, I don't have to put that control part in my hypothesis. I can say, if I get at least 8 hours of sleep, then I will do better on tests than if I get fewer hours. When I design my experiment, I have to design in a control. Good point. All right. Let's say that I'm stirring some sugar into water and I want to know how I can get my sugar to dissolve better or more sugar to dissolve in the water. I could say, if I heat up my water before I add the sugar, then more sugar will dissolve in the water. My point here is I want you guys to see the magic of the if-then format. It tells you what you're going to do, and it tells you what you're going to look for. So for our blacksmith experiment here, what is a, you can also test if you sleep. There's a lot of things we could do for testing sleep. Absolutely. There are a lot of things. Good point, Allison. So let's make a hypothesis for our blacksmith problem here. Remember, the blacksmith read this article that said there's a new kind of fuel that will make my fire burn hotter. That he asked the question, does it work? Now, what's the hypothesis in if-then format? Wick.
If I use this fuel, then my fire will not burn hotter.
Will not burn hotter. So you're going to try to disprove it in that way. Yeah. You could do it either way. You could write the experiment that said, if I use the new fuel, then it will burn at the same temperature as coal. Or if I use the new fuel, then it will burn hotter than coal. Or if I use the new fuel, then it will burn cooler than coal. You could write any of those. Any of those are valid ways to test your, to test this question that we had. All right, so let's look at this one. Let's focus in on this one. Let's say we want to know if the new synthetic fuel is used in a forge, then the fire will burn hotter. All right, now the examples that I've been giving you guys, I've used the personal pronoun I. If I get 8 hours of sleep, then I will do better on my tests. If I drink coffee, then I will take longer to fall asleep. In a true science experiment, we want to avoid using pronouns. We don't want to use I or you or he or she. We want to just state it like it's done. If this is done, then this will happen. So if the new synthetic fuel is used in a forge, then the fire will burn hotter. All right. Now let's look at the experiment next, because that's what comes after the hypothesis. What could we do? How could we test this hypothesis in an experiment? Nyla.
By buying the synthetic fuel and using it for their smithing, and then using the coal after and documenting how hot it gets.
Excellent. We would want to, as Wick said before, we want to compare it to what we're already using, what we're already doing, and see, does it really burn hotter than when we just use coal? Excellent. Now, couple things. You need to know 3 terms when we're talking about the experiment phase of the scientific method. These three things are called variables. So a variable is just something that could be changed in an experiment. And we have three kinds of variables: independent variables, dependent variables, and controlled variables. So let's look at each of them. The independent first, that's the thing that you change. Sometimes they call that the manipulated variable, but I'm going to call it the independent variable. The independent variable is something that the scientist changes. What are we changing in our experiment? Nyla?
The type of fuel.
A type of fuel. That's what we're changing. So that's our independent variable. The dependent variable then is what we look for. It's what we measure. It's the data that we collect. So in this experiment, what is our dependent variable? What are we going to be measuring? Wick?
The temperature of the fire.
Excellent. So we have our independent variable, the thing we're changing, the fuel. We have our dependent variable, the thing we're measuring, the temperature of the fire. And then we have everything else. And when we run any kind of a scientific controlled experiment, we want to only change the independent variable. We don't want any of the other things to change. All those other things are called controlled variables. Sometimes they're called constants or controls. Now, there are always a lot of controlled variables in an experiment. So basically, everything that we're not testing, we have to do this, we have to keep the same. So let's say we're using a big giant forge on a very cold day to test coal. And we're using a little tiny forge on a very hot day to test our new fuel. Can you see how we have too many variables that we're changing there? We're not going to know what's responsible for the temperature change, if there is one. We need to make sure both of the forges are the same size, the one used for coal and the one for our new fuel. The temperature is the same. The wind is the same. Even the person who's adding the fuel has to be the same in order to keep everything exactly the same. All right, now, can you think of some things that well, I'm going to skip that. So this is a silly but helpful way to remember the different kinds of variables. Those of you who have been in my classes before have seen this guy before. I'm sorry, I know he gets stuck in your head, but here we go.
Independent variables are the ones you change. Independent variables are the ones you change. Dependent ones are ones you measure. Controls will stay the same, whatever. Independent variables are the ones you change.
Okay, so there's a lot of words in there, but really all you have to remember is that first one. If you can sing that in your head over and over, independent variables are the ones you change, because you already know what controls are. They're the things you control. So if independent is the thing that you change, then dependent is what you measure. And that's an easy way to remember that. All right, so keeping those variables in mind, our independent variable is the one we change. It, in this case, is the fuel. The dependent variable is the things we measure. That's going to be the temperature of the fire. And then the controls are everything else. We're going to keep everything else the same. We can now conduct our experiment. This is where that if-then hypothesis is really, really helpful. If a new synthetic fuel is used in the forge, that's our experiment. We're going to use the new synthetic fuel in a forge. Then the fire will burn hotter. That's what we're going to look for. We're going to test the temperature of the fire. All right. If new synthetic fuel is used in a forge, then the fire will burn hotter. That's our hypothesis. Our experiment is trying the new fuel in the forge. Now it's time to collect our data. Our data will either accept our hypothesis or reject it. So let's take a look at what we mean when we say data. Basically, data is information that you get during your experiment. It's what you're measuring in the then part of your hypothesis. Whenever possible, we want to represent our data using a table or a graph or something that somebody could look at. So let's just say I have this right here. This is called a bar graph, and this charts the students' favorite juices and the number of students. So if I had a paragraph and the paragraph said 2 students prefer red juice, 8 students prefer orange juice, 10 students prefer yellow juice, and 6 students prefer purple juice. I mean, you could look at that, you could read that, but it makes a lot more sense if you put it in a graph. If you put it in this bar graph, you can see that. And when you get something like this one up top here that has a ton of data on it, then it is much, much easier if you have it in a graph. Now, there's a lot of different kinds of graphs that we can use in order to show data. There's just a few of them right there. I want to look at the ones that are most commonly used in science. So a line graph is one that we often use. So a line graph shows us small changes and patterns in data. So you can see here, this is rainfall in millimeters charted against the days of the month. So on the first day of the month, there were 5 millimeters. On the second day, there were 2, 12, 7, 8. We can see small changes in data, and we can see a pattern. We can see that it goes up and down. That's our pattern. Sometimes you'll see 2 lines, not just this one red one, there'll be another one. I have an example of that in a minute, which shows the relationship between 2 sets of data, where one set might rely on the other. So a line graph is commonly used in science. Wick.
Is this the one we're going to use for the velocity and time graph and the distance time
Are you
graph?
there already?
Yeah, I finished
yeah.
that lesson.
Yeah, we'll be using line graphs a lot when we talk about velocity and time. Yeah, so another kind of graph that we often use is called a circle graph. So there's another name for that. Sometimes it's called a pie chart. And it shows how one part relates to the whole, how one part is a percentage of the whole. So it is a round or circular representation, and each slice of the pie corresponds to its percentage, right? So a bigger piece of pie is going to be a larger percentage. So just looking at this, the pie chart tells us the cost of construction of a house. What is the major cost of construction of a house? What's the biggest one? Nyla?
Labor.
Labor, absolutely. Takes up 25%. When you have a pie chart like this or a circle graph, all of your percentages have to add up to 100, right? Because we're basing it on 100%. Another kind of graph that we sometimes use is called a histogram. We don't use it all that often, but it shows number ranges instead of like a set number. Wick.
For the pie chart, is it fine if you use degrees?
Degrees. Like what? Give me an example when you would use degree.
Like, okay, if the population on Earth, half of the people lived in America and the other half of the people lived somewhere else, then can I put 180 for America and 180 for other people?
No, you'd still want to use percentages. You'd use 50-50.
Okay.
It would be a line. I don't know how you would use degrees, because degrees, you got to have 180, in order to make a full circle. I see what you're getting
A
at.
full
that
circle is
is-
360.
I'm sorry, you're right. 360. Half would be 180. So yeah, you would use a circle graph with percentage to go with 100s. Good. All right. So histogram gives us a range between 4 and 8, between 8 and 12. This is probably my favorite kind of graph. I like scatter plots because I think they look like fun. Now, a scatter plot can give us a relationship between groups of numerical data. And it just looks like somebody scattered a bunch of dots on the top there. Now, one thing that's different than a line graph, we don't use lines to connect our data points. That would be chaos if we connected all these with dots. Instead, we use what's called a trend line. So the trend line goes right through the middle of the data. There's the trend line right there. You can see that. So we would say this data is trending up. If when we had our scatter plot, the ones were going down, we would say our data is trending down. Wick.
For the scatter plot, how do we determine the trend line?
So trend line is often, if you've got a computer, you can do it with a computer perfectly accurately. For when we do it, we mostly just, like if you're doing one for a lesson, you're going to mostly just estimate where it's going to be. You would not draw a trend line. Let me go back to this one right here, this one right here. If I said to draw the trend line, you would not draw a line that looked like that, right? And you wouldn't draw one that looks like this. you would draw your line kind of right through the middle. And they're not always straight lines. Sometimes a trend line will go up and then back down and then back up. It's just basically showing what the trend is over time. Good question. All right. Now, this one right here, this graph shows 3 sets of data. This is a line graph, right? It's a line. All the data points are connected with a line. And we've got it plotting plant growth rate over a 10-week period. Now, on what's called our y-axis, that's this one right here, right up and down like that. That's our y-axis. We have height in centimeters. We have time in weeks on our x-axis. So I want to show you guys a way, an easy way to remember what is the y and what is the x-axis whenever you have any kind of a chart like this. Picture a y like this and its long tail going down like that. That's the y-axis. If you can remember that's the y-axis, you can remember then that this one is the x. Okay, so picture that y with the long tail if you have trouble. All right, now, when we look at this, we want to know which plant grew the most. What is the plant growth rate over a 10-week period? Which plant grew the most? Now, when you first look at this, you might think it's A, right? Because if you look at the end, plant A, which is represented here in blue, right here, you might think that that's grew the most because it's at the top. But that's not what the question is asking. Wick.
Well, it didn't grow the most because it started at 30 centimeters. You have to check the start. And
Yep.
the red one actually grew the most because it started at 10 centimeters and all the way, it went to 95 centimeters.
Yep, you're right. Hold on just a second. Can you hear me now? When you said you can't, okay, good. All right. So yeah, you're absolutely right. So A right here, as Wick said, it starts at 30 and it goes to 100. So how many centimeters does it grow? Wick?
70 centimeters.
70 centimeters. And you always want to put your unit, your cm, because centimeters are a lot different than miles, aren't they? Or feet or meters. Yeah, so 70 centimeters. All right, look at B now. B is in red. B started at 10. See right here, starts at 10 and it goes up to about 95. So how much did B grow? Wick?
B grew 85.
85 centimeters. And what about C? C starts at 20 and it goes up to 60. So how much did C grow? Wick?
40 centimeters.
40 centimeters. 40 centimeters. So our question is, which plant grew the most? Had the most growth rate? What's our answer? Wick?
Wait, no, B.
Yeah, it would be B because B grew 85 centimeters. Yeah, exactly. All right. Now here's another one. So let's look at this. First, we need to figure out what exactly is this table asking for. It is asking, or what information does it give us? The information it gives us is the single day temperature for selected bodies of water in Arizona. What are the bodies of water that we're looking at? Fossil Spring, Lake Mary, and Verde River. We want to calculate the average temperatures. That's what the question is asking us to do. So how do I calculate an average of something? Wick?
You sum them all together and then divide by the number of numbers that you sum.
Exactly.
And I'm in
Exactly.
Arizona.
Oh, do you really? Have you been to any of these lakes?
No, we never go anywhere.
Well, maybe someday, Yeah, so what we're going to do to calculate the average of the Verde River single day temperature is we're going to add together 15, 20, and 19, and then divide by 3 because we have 3 numbers. If we had 5, we would divide by 5. If we had 10, we would divide by 10. You add them up and divide by the number of data points that you have. All right, now erase that off there. All right, so what goes in the question mark right there? How are we going to do that? We're going to add 19, 24, and 26. Wick, what are we going to get?
23.
We're gonna get 23. Now, one quick way to check your work whenever you're doing this kind of thing, I know this isn't a math class, but I'm giving you a little hint here. Look at your smallest number and look at your biggest number. Your average is gonna be somewhere in between them. So if you added this all together and then divided by 3 and you got the number 15, you know it can't be, because your average can't be smaller than your lowest number. If you got the number 40, can't be that either. Can't be bigger than your highest number. Has to be somewhere in between. All right. Now, this data table has different values. It doesn't have the same data because we are not, in this one, we were calculating the average temperatures. Now we're calculating the range of temperatures. So look there, the range of temperatures. You can see our numbers change, 19, 24, 26. This is 18, 23, 25. All right, always look at your table. Don't make assumptions that it's the same. So we're going to calculate the range in temperatures. Wick.
The range is 7.
Well, the range is 7 for 2 of them.
Yeah, for Lake Mary and Verde River, but the range is 0 for Fossil Spring.
Exactly, exactly. It doesn't change at all. Range is how much it changes from one day to the next. So Fossil Spring stays 22, so it has a 0 range in temperature. Never changes. This one goes from 18 to 25. That's 7. This one goes from 13 to 20. That's also 7. All right. So another kind of graph, or no, not another kind. The 2 most common ones. Probably the 2 most common ones that we're going to use in science are going to be bar graphs and line graphs. You see them a lot. Now, a bar graph, like I said, shows changes over time, or it compares things. This is going to compare all of these things to each other. And this compares these things to each other. All right, let me erase that. There we go. So here's our axes again. Remember that we're going to have our y-axis like this, and we're going to have our x-axis like that. Graphs are always going to have that. The x-axis usually is the time period or what is being measured, and the y-axis has numbers for the amount of stuff that's being measured. And these are good for when we're plotting data over long periods of time. Line graphs are used to show how something changes over time. It also has an x-axis and a y-axis. The x usually has the time period. So right here, this is the time. This is the number of days. This is the number of days as well, where the y-axis has what we're measuring. We're measuring degrees Fahrenheit in this one. And it is used when things are going to go up and down or collected in a short period of time. Or when you have 2 sets of data, or 3 or 4, like, you know, we saw the one that did kind of that. Wick.
Yeah, for this quiz, I accidentally put a capital V for vector instead of a lowercase one.
Okay, so I'd rather you'd ask questions about the quizzes privately write to me through Canvas inbox rather than in class. But I always give students one time to make that kind of mistake. So have I given you one before? Then you write to me and I'll give it to you once. I want you to learn to use good grammar, and we don't capitalize words in the middle of a sentence unless they're proper nouns. So I'll give it to you one time, and then from then on, if you put a capital where there shouldn't be one, or you don't put a capital where they should, that grade will stand. All right, now line graph and bar graph. Probably for our fuel question that we have here, the best kind of graph that we could use might be a bar graph right here. Now, consider this. Usually, when blacksmiths cook their coal, they cook it really hot until the impurities are burned off, and we end up with coke. It is a fuel that is almost 100% carbon, and it allows us to get up to somewhere around 3,000 or 4,000 degrees Fahrenheit at the core of the fire. So taking a look at this, see the coal and see the new fuel. If this was the result that we got, did the results support our hypothesis or not? Yes or no? Remember what our hypothesis was. If the new fuel is used in a forge, then the fire will burn hotter. Did the new fuel burn hotter? Yes or no? Nyla says yes. Anybody else? Come on, you guys can all vote. You got a thumb? You think yes or no? Yes, it does. You can see that the new fuel burn at, 4,500, a little more, those are a little bit off, but a little more than 4,500. Wick,
I mean, my technical old hypothesis was that it would burn less, so
Yeah.
that's why I put my thumbs down.
yeah, you're right. You're right. Absolutely. All right. But what if this was our result? If this was what we got, would it validate or invalidate our hypothesis? No, it would not. We would have to, if this is what we got, we would have to go back to the drawing board. We would have to go back and make a new hypothesis and start over again. All right. Now, after we've collected our data, the next thing that we're going to do is come to a conclusion based on our hypothesis. So in this case, what would our conclusion be? Quick.
I didn't understand which case because you showed us two cases.
Oh, okay. You're right. Okay, so for this one, this was our
Oh.
hypothesis.
Then
Right.
our hypothesis would be true, and we would say the new synthetic fuel, if used in a Ford, will burn hotter than coal.
Very good. Excellent. A lot of times when you're writing up a lab report, your conclusion will also include just a little summary of what you did. We did this, here's how we did it, just a real quick summary, and then you'll say what it is that you conclude. But there you go. Those are the steps of the scientific method. You make an observation, you ask a question, you do some research, you develop your if-then hypothesis, design and conduct your experiment, organize your data, and come to a conclusion. All right, we just have time to do one quick little test here. All right, let's suppose that, sorry, went one too far. Students of different ages were given a jigsaw puzzle to put together. The scientists wanted to see if the students' ages affected how long it took to put the puzzle together. What is our independent variable in that experiment? Wick.
The independent variable doesn't change, and the independent variable is the puzzle that they're given.
Nope, the independent variable is the one you change. Remember the song?
Oh,
Independent variable is the one you change. Nyla.
It's the student's age.
It's the student's age. So what's the dependent variable? Wick.
the dependent variable is the puzzle.
Actually, what are we measuring?
The time?
Yeah, it's going to be the time that it took them to do the puzzle. Right. The puzzle doesn't change, and the puzzle isn't what we're measuring. So it has to be one of our controlled variables. We have to control everything except the age of the students. And then, of course, we're measuring the time that they put together. They all have to be tested with the same puzzle. It wouldn't be a fair test if some of them had an easy 30-piece puzzle and others had a harder 500-piece puzzle. And it wouldn't help if somebody had a stopwatch that went fast and another one had a stopwatch that went too slow. So everything has to be the same. We have to have the same location, same temperature in the room, right? So the only thing that's different are the ages of the students. And with that, we're done. We're going to end class today. All right. Great job today, everybody. Anybody have any questions? All right. Have a great week. I'll see you next week. Bye.
Thank you. Bye.
Thank you. Goodbye.
Wick, do you have a question?
Yeah, so for the oral presentation, I read on the science part, I am kind of confused. Do we have to buy all the materials or